So this language, this L of M, the L of a Turing machine, the L of TM, if you like, TN big M is the label of this particular Turing machine. So L of big M is just the set of strings that the machine, the Turing machine, M, accepts. That's all it is. Okay? And any other string, the Turing machine would reject, presumably. In fact, we'll talk a bit about that. Well, this is the next session. What about the strings that the language does not accept? It leads to interesting complications. Anyway, all right. So so the language of the machine is just it's just the set of strings that the machine accepts. You know, it terminates in the accept state on that string. So all those strings for which that happens, that set of strings is the language of the machine, L of M. Okay. Okay. Another definition. Let me rephrase this slightly. So, a string of that language is recognized by the Turing machine. Recognize just means the Turing machine terminates in the accept state for that string. Okay, that's all. And we've used this term of a machine recognizing a string or language, actually a language. It recognizes the language means it accepts all the strings in that language. Okay, and rejects the others. It rejects all the others not in the language. So in that sense, the machine, whether it's a finite automaton, a PDA, or now a Turing machine, it recognizes the language. That means it accepts the strings in that language. Okay, if that hasn't penetrated, rewind. Okay, right. Okay, so the language is recognized by the machine. Okay, now Turing recognizable. So this is a particular kind of recognition. It's a language that a Turing machine can recognize. Okay, in other words, it's a set of strings that a Turing machine will accept. Okay, so you could I mean, now we've introduced this concept. You could talk, I suppose. This is not in the text. It's me saying this, but you could use a different kind of recognizable term. You could say FA recognizable, or finite automaton recognizable. You know, in other words, a language that a finite automaton can recognize. Or you could say a PDA recognizable. That would mean a language that PDA could recognize. Well, here we're talking Turing recognizable. That's a language, a kind of language that a Turing machine can recognize. Okay, so a language is said to be Turing recognizable if some Turing machine recognizes it. Okay. Right. So, all right. Now things start getting a little bit philosophical, a bit more fun. All right. Okay. So you input. You position your Turing machine header at the beginning of, well, so let's say the left-hand symbol of your string at the beginning, and you switch it on in a sense, and off it goes. Okay. So how can it finish? I mean, sorry, wrong word. Three. See, it gets philosophical. Finish. What does that mean? Three things can happen. Well, and what does happen mean? It really does get philosophical. Okay, so three things can happen. Three outcomes. Well, even that, again, same query. If you have a philosophical turn of mind, you may be interested in this sort of thing. So three outcomes. You switch on the machine, and what can happen? Well, it can accept, right? No problem there. It just accepts the string and switches off in the accept state. It can reject. Similarly, it rejects the string and switches off. Goes to the reject state, switches off. Okay. And this third, now this is new. It loops. Now what does that mean? Well, basically it just means it doesn't halt. Yeah, I can hear the alarm bells going off already. Okay, in your mind, if you like philosophical puzzles, what does that mean? What does it mean not to halt? Okay. Now, if you're a programmer, you know you can get in infinite loops that it's impossible to get out of unless you break it somehow. So in effect, we're talking about like the situation of like infinite loops, where like recursion. If you're a computer guy, recursion without checking on the boundary conditions. Like a program calls a procedure calls another procedure, which calls the same procedure again, which calls itself again, which calls itself again. It could go on infinitely. It would just loop, like an infinite loop, unless in the procedure itself is some kind of check, and each time the procedure calls itself, it's passing some integer that gets decremented, that gets diminished by 1 each time it calls through. It makes a call to itself. So it's passing a call to itself and this integer, this counter, if you like, which counts down until eventually a procedure gets called with an integer small enough that the procedure is no longer called. It just returns some simple answer. Well, something like that. So this kind of loop here is an infinite loop, right? So that the machine either accepts, rejects, or goes into an infinite loop. It loops. In other words, it doesn't halt, in the sense that cannot halt. Okay. Now, this looping, it might be some simple or complex behavior that never, because of the way it's set up, the nature of the program, if you like, in other words, your transition rules, is set up in such a way that it can, it just never leads to a halting state. In other words, it never leads to a state that is queue accept or queue reject. Okay, that could happen. So it loops in that sense. And remember, a Turing machine never halts. Put it another way, the Turing machine just keeps going until it stops by transitioning into the queue accept or the queue reject. But if that never happens, if it never transitions into one of those two states, a halting state, well, it just keeps going, it just loops, okay? Like infinite loop, right? Okay, so how can a Turing machine fail to accept, meaning that it does not accept? Well, there's two ways, right? There's only three cases: accept, reject, and loop. Okay, so if it's not accept, well, it means it's one of the other two, right? So either it rejected or it looped. It looped, past tense. Again, same problems, right? Okay, so failing to accept, that means, the two possibilities. Either it went into the queue reject, the state went to queue reject, and switched off. So rejected the string, okay, or it looped. It's looping. Now here's a comment. Interesting. It's when your philosophical alarm bells went off, I suppose. How do you distinguish the two situations? One, you're in a genuinely infinite loop where, just given the nature of the transition rules, the program, if you like, it's just impossible for the program ever to transition to an accept state or a reject state. That's one possibility, causing the looping. But another possibility is how do you know? I mean, you wait and you wait and you wait for your Turing machine to accept or reject, in other words, to stop, and you wait and you wait and you wait. How do you know that you're in an infinite loop, or it's just taking a hell of a long time? It's just like, when we do part 3 of the textbook, we'll be talking about complexity, and some problems are just enormous. They require enormous amounts computing capacity. So how do you know you're not in that situation, right? So you need to distinguish between can never halt, because it just can never get into a halting state, queue accept or queue reject, or it's just taking a hell of a long time. How do you know? So on that question, we'll go to the next session.